Option D, energy in the environment. Okay. So, solar constant defined as the intensity of electromagnetic radiation from the sun just outside the Earth's atmosphere. State what is meant by intensity and give a suitable unit. So, intensity is the power incident per square meter or per unit area. And it's in watts per square meter. Yeah, so radiation power incident per unit area. Technically it's perpendicular, but I think that's fine. Assuming the sun behaves as a black body, show that a value for this intensity can be calculated using this. So that black body bit suggests that the power will be equal to that. What else do we need? We've got Wien's constant in there. So, and lambda is the wavelength of, so that's lambda peak. So we can also say that temperature is Wien's constant over lambda. In addition, we can say that intensity is equal to power over 4 pi d squared, which, yeah. So all we've got to do is smash these expressions together into that. No real problem. Therefore, intensity is going to be equal to sigma. This is surface area of a sphere, so it is 4 pi radius of the sun is lowercase r, so 4 pi r squared times t to the 4, but we're going to sub in w over lambda to the 4, and we're going to divide that by 4 pi r. We're given as the distance, r squared. So 4 and the pi are going to cancel out of our expression. We're going to be left with r squared w4 over r squared lambda 4. Yeah, okay. Only 2 marks. It surely doesn't need more than that. I think it's just you're getting your marks for recognizing which, what the implication is of this black body, what equations this comes from, and maybe 1 for kind of the substitution or something like that. Calculate the value of the solar constant given that r is equal to that, and big R is equal to that, and lambda is equal to that. 2 marks for this, but I mean, really, it doesn't seem like this. It just seems like a direct substitution, surely, but I don't know. Be a bit careful. That many kilometers. We want to use meters, really. I mean, technically, because we've got r squared over r squared, it's actually not gonna matter, but I am gonna put it in meters anyway, just because I do. That's what I do. Multiplied by sigma is Stefan-Boltzmann constant, 5.67 times 10 to the minus 8. W is Wien's constant and is 2.9 times 10 to the minus 30. Oh, I'm gonna have to check. If in doubt, why wouldn't you check? Really, why wouldn't you 2.9 times 10 to the minus 3. That is power 4. Goodness me. All over, and then this squared, 150 times 10. And again, I'm going to put it into meters. So that's times 10 to the 9. That is also squared, and then times lambda to the 4. I'm going to put lambda into meters as well. So 500 times 10 to the minus 9. Sorry about the handwriting here. And that is power 4. That is a big old thing to be putting into the calculator. So it's very much the sort of thing that I'd be tempted to do twice. But then maybe that's just me. Just because it just feels like there's so many opportunities to completely muck this up in the, in transferring it to your calculator. 2.9 minus 3 to the power 4. Always freaks me out the way the calculator just kind of shows the minus 3-bit raised to the power 4, and I don't have confidence that it's going to do the right thing for me, but I'm sure it is. 150 times 10 to the 9, and that is squared. And then finally 500 minus 9 to the 4. Hopefully I'll get a number that I recognize. 1380. I actually do recognize that. About a kilowatt or 1.3 kilowatts per square meter, I think is pretty standard accepted number. So that does look right. So all good. Okay. Pumped storage hydroelectric. We've got a high reservoir, we've got a low reservoir, we've got a flow of water generating electricity. It's all good. Low demand, this much water is pumped up to the high level reservoir. Gives us a height difference. Calculate the mean power required for this process, and we're given the density of water is 10 to the 3 kilograms per cubic meter. So mass per second. Oh, that's atrocious, isn't it? Oh, I think it's actually not me. I think my battery's going on my little pan here. I think that's what's happening, or something's happening. There's definitely something happening, but I don't. Why can't I? It's not letting me delete that. I don't even know what's happening. What's going on? No, won't let me rub out. I'm not sure why. Sorry about this, folks. And yeah, not sure if it's the pan or well, this is, oh great, now it's like opening stuff in the, what? Come on, computer, you've got this. Apparently it really oh my goodness, maybe it isn't the pan. Maybe my computer has absolutely cacked it there. I don't know what on earth is happening. So mass per second equals 40 times 10 to the 3 kilograms per second. And this is just MGH. So energy per second. Whoops. Energy per second required is equal to mg delta H, mass per second times g delta H equals that number that we've just calculated, the mass per second, multiplied by 9.81, multiplied by 390 meters. So the rationale here is straightforward. Power is energy per second. If we were just moving 40 cubic meters of water as a one-off, we could calculate the change in gravitational potential energy. If we're moving that every second, then it's that much energy per second, which is therefore a power. And 1.53 times 10 to the 8, that is quite a lot. $153 megawatts. That is pretty robust. Discuss the impact that pump storage power stations have on greenhouse gas emissions. Well, I mean, arguably, pump storage is useful because it means that we don't waste energy. If we're producing an excess of electricity, this is a way of storing that energy rather than wasting it. So irrespective of how that electricity has been produced, that obviously saves energy. And if you're saving energy, then you're saving the need to burn fossil fuels elsewhere to produce emissions. There's 3 marks here, so I feel like we need to make 3 points. This on its own does not produce, doesn't produce any CO2 or anything like that. So does not produce CO2 when in use. However, CO2 may be produced in generating electricity to pump water up. Anytime it says discuss, you kind of want to give points for and against, if you like. You don't want to give a completely slanted argument. So it doesn't produce CO2 when in use. CO2 may be produced in generating electricity to pump water up. However, since it stores energy, so prevents waste. Prevents wasted energy and reduces demand for sort of production that might produce more CO2. Demand for, what am I saying? Not supposed to say and, it's supposed to be one of those. And reduces demand for production that might produce CO2. So I've made 3 points. It's 3 marks. I think that's probably okay. Other things you might say, arguably, these things are made out of a huge amount of concrete, and concrete actually produces quite a lot of CO2. So maybe, when you're building it or something like that, you could argue that it produces a fair amount of CO2. To be fair, most power stations use quite a lot of concrete though, so I'm not sure if that's a good point. Right, the triple product. Okay. Yeah, this is going to be pretty dubious. I'm not sure how much of this I can remember. Explain confinement time. So, yeah, explain what is meant by the confinement time of the fuel. As I recall, that is the time that the fuel remains above fusion temperature, isn't it? I think confinement time. It's a slightly misleading term. It's not how long the fuel is confined for. It's how long it's above the energy requirement for fusion. The time fuel must be above temperature required for fusion. So fusion triple product of that at a temperature of 1.1 times 10 to the 8 Kelvin. So that is pretty hot. We're at about 100 million Kelvin there. Show that this temperature is equivalent to a particle energy of about 10 keV. So mean particle energies are approximately kT for plasmas and such, rather than 3/2 kT that you would use in an ideal gas law. So mean particle energy is approximately kT, and kT is equal to K. It's just the Boltzmann constant, 1.38 times 10 to the minus 23 multiplied by this temperature. So 1.52 times 10 to the minus 15. That is, of course, in joules. So to turn that into electron volts, we're just going to divide by 1.6 times 10 to the minus 19. Looks like that's going to give us about the right answer. Sorry, that is 19. So 9.5 times 10 to the 3. Actually. EV, which is approximately 10 keV. Hence determine the value of the confinement time required if the particle density is that. So from memory, confinement times are of the order of a second or two. Right, so yeah, so NT, yeah, so it's told us that the triple product is times 10 to the 22. We're given n, and we're given the temperature. Yeah, that is a big so particle physics. Look at these units. Be really careful here. In particle physics, temperatures are given in electron volts. So yeah, that's why there's a hence at the start of this. So we've got to be really careful here. This temperature that we'll put into the triple product is not the temperature, is not the Kelvin temperature. It is not the Kelvin temperature. It is the particle energy, I think. So I think our confinement time should be equal to 8.0 times 10 to the 22 divided by n multiplied by this yeah, I have some memory of that in particle physics and plasma physics and stuff. Energies are temperatures are just given in EV. If you look at the units of this, is kind of a giveaway. that the units of this, you know, meters minus 3, that is a density, that is a particle density. And yeah, then it's kilo electron volts. Yeah, there's no Kelvin in these units whatsoever. So I am pretty sure that's what we need to do here. Soon find out if I get a ridiculous answer. I've got 4.2 times 10 to the minus 3. That seems far too short. That doesn't seem sensible at all. So maybe I'm... Oh, but it would be so much... It would be way worse if I... It'd be... Oh, I'm an idiot. I am an idiot. Look, these units are in keV. They're already in keV. I don't need this. I don't need the times 10 to the 3. 4.2 seems awfully long. I thought these things were normally... I thought it was normally about 1 second, but... I'm just checking my answer. Yeah, 4.21 is what it comes out as. I'm not sure. I might have to double check this stuff. I do apologize. I might just have to check that I've done that right. But if I use the Kelvin temperature here, that is definitely wrong, because the Kelvin temperature here at 10 to the 8, you know, we'd be in the microsecond zone, and units wise, this would have weird units. It would be problematic. It wouldn't have units of seconds, that's for sure. Okay, I think that's right. 2 layers of equal thickness form... Bit of a topic shift. 2 layers of equal thickness form the external wall of the building as shown. Thermal conductivity of the inner layer is 0.1 watts per meter per Kelvin, and that of the outer layer is 0.5 watts per meter per Kelvin. Yeah, okay. Tom states the temperature at the boundary is that, and that the rate of heat flow per unit area is 90 watts per square meter. To determine if he's right. So, yeah, what we're after here is this equation on the right hand side, isn't it? I believe delta Q delta T is equal to minus AK delta theta delta X. I think so. Rate of heat flow is equal to area times conductivity multiplied by the temperature gradient is what we should be after here. So what we can say is if I have heat flowing through this, the boundary layer in between has whatever amount of heat flowing through it, but the same amount of heat that passes through the first layer must pass through the second layer. So what I can do is I can say, what can I say? That the rate of change of heat flow is equal for the 2 layers. It has to be. I have to have the same amount of heat flowing through the 2 layers. So then I can write an expression for this in terms of change in temperature. I think that is going to be correct. So delta Q over delta T, same for both layers. Sorry, it's such a long time since I've done this stuff. I don't get much practice with this, so I apologize for not being a little bit sharper on it. So what I can say is minus A times 0.1 watts per meter per Kelvin times delta theta. So I've got 20 degrees minus whatever the temperature in the middle is, over 10 centimeters over 0.1 needs to be equal to minus a times 0.5 times, and in this case it will be, oh, that's nice, isn't it? Sorry, theta minus 5 is the temperature difference on that side over 0.1, and then I can cancel out the a's and the 0.1s there, etc. And yeah, if I'm just going to go ahead and multiply as well both sides by 10 to get 20 minus theta equals, I'm going to multiply it by minus 10 in fact, 5 theta minus 25. So yeah, 45 equals 6 theta, so theta equals 7.5. So he is correct. That is so correct. And now that we've got that, it's straightforward to go back and calculate dq per dt. He's doing this per unit area, so no problem there. dq per dt per area will just be equal to, therefore, minus k delta theta delta x, and it doesn't matter which one we choose because it's got to be the same for both. So if we just choose that first one, I've got minus 0.1, delta theta is 20 minus 7.5, thickness is 0.1 conveniently, so that is, the 0.1s are going to cancel, so that is minus 12.5 watts per square meter. So no, he's not correct. I think that's it. Sorry, it was a little bit shaky at times. Maybe you never know. You might never hear this because I might record that again and try and do a better job of it. Anyway, that's it.